What would it feel like to stand on Teegarden's star? If you woke up on Teegarden's star B tomorrow, what would the sky, the air, and the ground actually feel like compared to Earth? We talk about habitable planets all the time, but we rarely stop and ask a much more intimate question. What would it be like to stand there, to look up, to breathe in, to feel that alien world under our feet? In the hunt for alien life, that is the question that turns distant data into a place we can almost touch. So, let's begin with the sky. Above you, there is no bright yellow sun tracing an arc from horizon to horizon. Instead, Teegarden's star hangs as a dim red ember, frozen in almost exactly the same spot day after day. This planet almost certainly keeps one face locked to its star, its rotation matched to its orbit, so the sun never rises and never sets. It simply glows, a deep crimson coin in a permanent, eerie twilight. But while one hemisphere bakes in endless day, the other is trapped in eternal night. On the far side, that same star is forever below the horizon, leaving a sky of hard, cold starlight. Between these two extremes lies a narrow band, a ring of perpetual dusk, where the star hovers near the edge of the sky. If Teegarden's star B is truly habitable, this thin twilight zone may be where life clings on. What would the air feel like there? That depends on an atmosphere we have not yet seen. Optimistically speaking, if the planet carries a thick, Earth-like blanket of gases, you might feel a mild, steady wind flowing from the hot day side toward the frozen night. The light around you would be dim, more like standing outside just after sunset, with colors shifted toward deep reds and infrared that human eyes cannot fully see. This means plants, if they exist, might be dark and heat-hungry, soaking up every last photon from a feeble red dwarf. It should be noted that Teegarden's star B is a paradox. By mass and by the energy it receives from its star, it could be strikingly Earth-like. Yet its host star is so faint and so small that we only discovered it in 2003, quietly slipping through our cosmic backyard just 12.5 light-years away. How many other worlds like this have we missed in the darkness?
And this is where the stakes rise. We are not just asking about one planet in one obscure system. We are asking whether worlds around tiny red dwarfs, the most common stars in the galaxy, can ever truly be home. If Teegarden's star B, with all its promise, turns out to be hostile, what does that say about our chances elsewhere in the universe? So it's time to find out the truth. Is Teegarden's star B the closest thing we have to a second Earth, or a beautiful, deadly mirage that only looks habitable from far away? Why this invisible star might decide our cosmic future. To understand why this one invisible planet matters, we have to zoom out. In the hunt for alien life, Teegarden's star B is not just a curiosity. It is a test of the most common kind of neighborhood in the entire universe. Red dwarfs like Teegarden's star are everywhere. They make up around 3/4 of all stars in our galaxy. But while the majority of people imagine life around sun-like stars, the statistics say otherwise. If life is common, then most of it should be circling these small, cool, dim embers. This means that every time we study a potentially habitable planet around a red dwarf, we are really asking a much bigger question. Are most of the galaxy's Goldilocks zones actually friendly to life, or are they cosmic traps? Teegarden's star is a perfect example of this hidden majority. It should be noted that it is only about 12.5 light-years away, practically next door in cosmic terms, in the constellation Aries. Yet you will never see it with your naked eye. It is so faint that astronomers only identified it in 2003, not because it suddenly appeared, but because its tiny red glow was buried in the background. The star slipped past us for decades, right in our local cosmic backyard. And orbiting that faint ember is Teegarden's star B. Discovered in 2019, it has a mass very close to Earth's and completes an orbit in just under 5 days. That sounds extreme, but remember, this red dwarf is much cooler and dimmer than the Sun. So despite the tight orbit, the planet receives roughly Earth-like energy. Optimistically speaking, that puts it squarely in the star's Goldilocks zone, where liquid water could exist on the surface. On paper, it looks remarkably Earth-like.
That is exactly why this system is such a crucial test case. Earth-sized mass, Earth-like insulation, right in the habitable zone of a nearby red dwarf. For climate and habitability models, Teegarden's star B is almost a laboratory experiment set up by nature. If we cannot figure out a planet this ideal, what chance do we have with more exotic worlds? But here is the tension. Depending on a few key unknowns, the same basic planet could be a temperate, ocean-covered world with a thick, protective atmosphere, an airless, frozen rock where water is locked as ice in eternal night, or a runaway greenhouse, hotter than Venus, with steam-choked skies. Which version is real? Right now, our models can support all three. So it's time to find out the truth. In the next part, we will dive into the star itself, the tight orbit, and the strange climate patterns of a tidally locked world. We will imagine how alien life might adapt to a dim red sun, and what alien astronomers there would see when they look back at us. And then, we will ask a harder question. What can our telescopes actually prove, and what might forever remain just out of reach? From TRAPPIST-1 to Teegarden star, the new frontier of tiny suns. So if TRAPPIST-1 has forced us to rethink what a habitable planet around a red dwarf looks like, where do we look next? In the hunt for alien life, which tiny sun becomes the new test case for everything we still do not understand? For a while, the poster children were clear. Proxima Centauri b, just over 4 light-years away, grabbed headlines as the closest potentially habitable exoplanet. Then, TRAPPIST-1 arrived, with 7 Earth-sized worlds packed so tightly that from one planet, the others might loom larger than our moon. These systems showed us that small, cool stars can host surprisingly rich families of rocky planets. But while they raised our hopes, they also raised a brutal question. Are these worlds actually friendly to life, or just Earth-like on paper? Teegarden's star quietly steps into that spotlight. It should be noted that this is another ultra-cool red dwarf, even dimmer than TRAPPIST-1, and far less massive than our Sun. Only about 1/10 of its mass. It is just 12.5 light-years away, practically in our astronomical backyard, yet so faint that we only discovered it in 2003. This means there could be many more such stars hiding in the dark, each with their own compact planetary system. Now compare the numbers. Earth orbits at 150 million kilometers, taking 365 days to complete a year. Proxima Centauri b whips around its star in about 11 days. TRAPPIST-1's planets complete orbits in a few days to about a week and a half. Teegarden star B goes even further. A year there lasts roughly 4.9 Earth days. From above, its system would look like planets drawn in, almost on top of the star, huddled close around a dull red ember. But while the orbits are extreme, the energy is not. Because Teegarden's star is so cool and faint, Teegarden's star B still receives roughly Earth-like stellar flux. Optimistically speaking, that places it right in the Goldilocks zone, where liquid water could exist. On paper, its minimum mass is close to Earth's, its temperature could be temperate, and its star appears relatively quiet for a red dwarf. If TRAPPIST-1 gave us a laboratory full of rocky worlds, Teegarden star B looks like the clean, simple experiment we have been asking for. Here is the pattern interrupt. JWST is already dissecting TRAPPIST-1, weighing in on atmospheres and surface temperatures. But for Teegarden star, we mostly have theory, not data. So it's time to find out the truth. If TRAPPIST-1's planets are turning out harsher than we hoped, stripped of thick atmospheres, and baked or frozen by their star, does Teegarden star B break that pattern, or confirm our worst fears about red dwarf worlds?
In the next section, we will zoom in on Teegarden star B itself, its orbit, its possible atmosphere, and what a day, if we can call it a day, might feel like under that dim, red sun.
Meet Teegarden's star, the tiny ember next door. So if Teegarden's star B might be our best nearby test of a truly Earth-like world, what kind of star is bold enough to host it? To answer that, we have to meet the tiny ember next door. Teegarden's star is what astronomers call an ultra-cool red dwarf, and it really earns that title. It should be noted that this star has only about 1/10 of the Sun's mass and is only slightly larger than Jupiter in size, yet far more massive. Its surface is much cooler than the Sun's, so instead of blazing white-yellow, it glows a deep, dull red in visible light and shines most of its energy in the infrared. In the hunt for alien life, this kind of star is both incredibly promising and deeply strange. Here is the surprising part. Despite being one of our closest stellar neighbors, only about 12.5 light-years away in the constellation Aries, Teegarden's star was discovered in 2003. Why so late? Because it is faint and fast. Its light is so weak that even nearby it hides in the background, and its high proper motion means it slides across the sky from year to year, almost like it is trying not to be noticed. This means that even in our local cosmic backyard, we are still finding stars that were effectively invisible to us just a few decades ago. How faint is it exactly? Compared to the Sun, Teegarden's star emits only a tiny fraction of the light, thousands of times less luminous overall. If we swapped our Sun for Teegarden's star without moving Earth, our planet would plunge into a deep, permanent ice age. So, for liquid water to be possible, any habitable planet has to move in extremely close, deep into a tight Goldilocks zone pressed right up against the star. Teegarden's star B orbits in just under 5 days, yet still receives roughly Earth-like energy from its star. A year there would pass between 2 weekends. But while the star is small and faint, it is also old and remarkably stable. The best models suggest Teegarden's star has been burning quietly for many billions of years already. And because red dwarfs sip their fuel so slowly, it could continue shining for hundreds of billions of years more. Optimistically speaking, that is an almost absurd amount of time for a planet to remain potentially habitable.
So it's time to find out the truth behind the central irony here. A star too dim to see with your naked eyes might host one of the most Earth-like planets we have ever detected. If we nearly missed this nearby system, how many other quiet, infrared embers are hiding entire families of worlds? In the next section, we will zoom back in on Teegarden's star B itself and ask what life would actually experience under that deep red sun. The tools we have now, how we found Teegarden star B without seeing it. So if Teegarden star B might be one of the most Earth-like worlds we know, how did we find it without ever seeing it cross its star? We did it by watching the star itself wobble. When a planet orbits a star, the two actually orbit a common center of mass. The planet swings wide, but the star also moves in a tiny counter-orbit. From our vantage point, that motion shows up as the star very slightly moving toward us and away from us, over and over again. This means the star's light is minutely stretched and squeezed, a pattern we can measure as changes in velocity of just a few meters per second. TRAPPIST-1's planets reveal themselves by transits, as dips in starlight. But while that system conveniently lines up edge-on, Teegarden star does not. We do not see Teegarden star B pass in front of its red dwarf host, so there is no neat, repeating shadow to measure. Instead, astronomers turn to high-precision spectrographs, like Carmenes in Spain, along with similar instruments on other telescopes, to dissect the star's spectrum night after night. In the hunt for alien life, this is one of our sharpest, but also most indirect tools. Carmenes splits the starlight into thousands of narrow wavelength channels and times their shifts with extraordinary care. Teegarden star is low mass and faint, but its planets tug on it strongly enough that we can detect velocity swings of only a few meters per second, walking speed on Earth. From the timing of those wobbles, we infer an orbit of about 4.9 days for Teegarden star B, placing it squarely in the Goldilocks zone of this cool, dim system.
However, radial velocity gives us mass in a very particular way. It should be noted that what we actually measure is a minimum mass, because we do not know the exact tilt of the orbit relative to our line of sight. If the orbit is inclined, the true mass is a bit higher than the minimum. Yet even with that uncertainty, the best fit value for Teegarden star B is very close to Earth's mass. That strongly suggests a rocky, Earth-like planet rather than a puffy mini Neptune wrapped in a deep hydrogen envelope. But here is the catch. Without a transit, we do not know its radius. No radius means no direct density and no chance yet to separate a bare rock from an ocean world or a thick Venus-like atmosphere. We also lack atmospheric spectra, the fingerprints of gases that JWST has started to collect for the TRAPPIST-1 system. So it's time to find out the truth with the next generation. Future giants, like the extremely large telescope, may be able to tease out reflected light or thermal emission from planets around nearby red dwarfs. And if Teegarden star B ever does reveal a grazing transit, instruments like JWST could finally turn our models and educated guesses into a detailed portrait of a real, possibly habitable world. Optimistically speaking, the numbers we have now are just the prologue. Next, we will step onto that unseen surface and ask what life would actually feel under that dark red sun. A planet on a 4.9-day year, the orbit that changes everything. So if the numbers are just the prologue, what kind of clock is this world actually running on? Because before we talk about oceans or alien forests, we need to understand Teegarden star B's very strange year. Teegarden star B races around its red dwarf in just 4.9 Earth days. That is its entire year. In the time it takes us to get through a long work week, this planet has completed a full loop of its orbit, and New Year's has already come and gone. It should be noted that this orbit is incredibly tight, only a tiny fraction of the Earth-Sun distance. So let's begin with a simple picture. Take our solar system and zoom all the way into the inner regions. Mercury, the closest planet to the Sun, orbits at about 0.39 astronomical units. Now shrink things even further. Teegarden's star B's entire orbit would fit comfortably well inside Mercury's path, hugging its star like a hot inner ring. Yet somehow, despite being so close in, it is not automatically a scorched wasteland. How is that possible? This means we have to think not just about distance, but about the star itself. Teegarden star is an ultra-cool red dwarf, far dimmer and cooler than the Sun. It puts out much less total energy, shifted more into infrared. So a planet has to snuggle in close to receive the same power per square meter that Earth gets. The remarkable result is that Teegarden's star B, on its 4.9-day orbit, likely receives roughly Earth-like stellar energy. In the hunt for alien life, this is exactly the kind of configuration that catches astronomers' attention. It places Teegarden's star B right inside the star's Goldilocks zone,
the region where a rocky planet could, in principle, host liquid water on its surface. But while habitable zone sounds almost definitive, it is not a promise of oceans. The atmosphere has to cooperate. Too thick, and you get a Venus-like hothouse. Too thin, and you freeze. There is another consequence of that tight orbit we cannot ignore. At such close distances, tidal forces are strong. Over millions of years, they act like a cosmic brake, slowing the planet's rotation until one side always faces the star. Optimistically speaking, Teegardens star B is very likely tidally locked, one hemisphere in endless day, the other in permanent night. So what does time feel like on a world with no sunrise or sunset? Instead of a cycle of days, you have geography. A blazing dayside under a fixed red sun, a frozen nightside under eternal stars, and between them, a narrow twilight band, the terminator. This dim ring, where the star hovers forever on the horizon, could be the most habitable region of all, if winds and oceans can shuffle heat around.
So it's time to find out the truth. Does this extreme orbit create a stable, life-friendly climate, or a world split between inferno and ice? In the next section, we will walk that twilight line and see how Teegardens star B's skies might actually look and feel. Two futures for Teegardens star B: oasis or airless rock. So if the twilight line might feel surprisingly Earth-like, what kind of world are we really talking about here? In the hunt for alien life, Teegardens star B seems to sit on a knife edge between two radically different futures. Is this planet a temperate, ocean-bearing oasis with a thick, protective atmosphere? Or is it an airless, irradiated rock, stripped bare by its red dwarf star and frozen into silence? There is almost no middle ground. The same orbit that places it squarely in the Goldilocks zone also exposes it to the full fury of its host star's youth. Optimistically speaking, Teegardens star B could be one of the most habitable planets we have ever inferred. Imagine a robust atmosphere, perhaps similar in pressure to Earth's, swirling endlessly between the day and night sides. Winds would haul heat away from the substellar point and redistribute it around the globe. In the permanent twilight band, temperatures could hover around the melting point of water, allowing stable oceans, clouds, and even rain. In that scenario, the red dwarf above would glow as a deep ember fixed in the sky. But the climate beneath could be surprisingly mild. Infrared-rich light would feed strange photosynthetic chemistries. Thick air would scatter and absorb radiation, and perhaps a magnetic field would deflect the worst of the stellar wind. This means Teegardens star B would not just be technically habitable, but comfortably so, at least in that ring of eternal sunset. But while that picture is enticing, there is a darker possibility. Early in the life of a red dwarf, flares and intense particle streams can be brutal. If Teegardens star was more active in its youth, repeated blasts of high-energy radiation could have eroded the planet's atmosphere faster than it could be replenished. Without sufficient gas, there is no shield, no pressure for liquid water, and almost no way for life to cling to the surface. In that pessimistic case, the dayside might be a scorched, bare rock, heated directly by the star, with no clouds to soften the glare, while the nightside collapses to cryogenic cold. The temperature contrast would be extreme, the surface constantly bombarded by radiation, and the only ocean would be a vacuum above a desiccated crust.
It should be noted that from far away, both futures could produce very similar mass and orbit measurements. The difference lies in invisible details. So what decides between oasis and wasteland? Tiny shifts in initial conditions, the strength of the planet's magnetic field, how many volatiles it started with, how violently the star behaved in its first few 100 million years. So let's begin to peel back those layers. In the next sections, we will move from the star's past tantrums to the planet's climate physics. And so it's time to find out the truth about which fate Teegarden star B most likely chose. Who we are and where we're going in this journey. So as we peel back those layers, who is this we doing the peeling? And where exactly are we heading in this journey? We should be clear about that before we dive into the deep end of Teegarden stars physics. On this channel, we live in the hunt for alien life. We have already walked through the crowded TRAPPIST-1 system, weighed the chances of Proxima b surviving its violent red dwarf parent, and compared a whole zoo of Earth-like exoplanets in that tight Goldilocks zone around small stars. It should be noted that everything we are about to do with Teegarden star B builds on those earlier deep dives, but you do not need to have seen them to follow along here. Here is the roadmap. First, we will understand the star itself, Teegarden star as an ultra-cool red dwarf, how it compares to TRAPPIST-1 and Proxima Centauri, and why such a faint ember of a star can still power a potentially habitable world. Then, we will move outward to the orbit of Teegarden star B, its 4.9-day year, and what tidal locking really means when one side of a planet may face the star forever. At each step, we will ask, does this make the world more or less friendly to life? Next, we will translate that orbit into climate. We will explore several atmosphere scenarios, from a thick, heat-redistributing blanket that keeps the night side from freezing solid, to a thin, fragile shell where air, and even oceans, might start to collapse onto the dark hemisphere. What would it feel like to stand in the permanent twilight ring between scorching day and frozen night? Would that narrow band be the true Goldilocks zone on the surface? After that, we turn to life itself. We will imagine how alien organisms might adapt to a sky dominated by deep red and infrared light, whether infrared photosynthesis is realistic, and which biosignature gases could build up in such an atmosphere without being destroyed by flares. Optimistically speaking, could Teegarden star be host a lush, dimly lit ecosystem? Or are we looking at a marginal refuge clinging to the Terminator line? Finally, we will ground all of this in real data. We will look at what telescopes like JWST, the Extremely Large Telescope, and future missions can actually test. Atmospheric composition, temperature maps, maybe even hints of clouds. This means we are not just daydreaming, we are sketching predictions that the universe itself can confirm or rule out. Do not worry about the complexity. We will start with simple pictures, like imagining Earth tidally locked to the sun, and only then build up to ideas like atmospheric collapse and exotic photosynthesis. You will not need a physics degree, only curiosity. And all the way through, we will keep coming back to our guiding question. Would each of these ingredients make Teegarden star be more or less welcoming to life? So, let's begin. Why tiny red stars are so tricky for life. So if all we need is curiosity, what exactly are we up against with a tiny red sun? Because before we fall in love with an Earth-like planet in the Goldilocks zone, we have to face an uncomfortable truth. Red dwarfs are both our best bet and our worst nightmare in the hunt for alien life. Red dwarf stars absolutely dominate our galaxy. They are the quiet, background population of the Milky Way, small and faint, yet making up around 3/4 of all stars. Even Proxima Centauri and TRAPPIST-1 belong to this family. This means that statistically, most potentially habitable planets in the universe will orbit these dim, cool stars. But while that sounds promising, there is a catch. Their Goldilocks zones are so close in that any habitable planet must huddle right next to the star, where stellar tantrums matter a lot. So what makes them controversial homes for life? In their youth, many red dwarfs are extremely active. They blast their planets with powerful flares, high-energy radiation, and dense stellar winds. A planet that orbits in just a few days, like Teegarden star B, never gets to sit at a safe distance. It lives right under the blowtorch. The fear is simple. Could this early onslaught strip away an atmosphere before life even has a chance? To untangle this, we need to separate the problem into two layers. First, what the star does. Second, what the planet can do in response. The star sets the rules of the game. Its light spectrum, how often it flares, how strong its winds are, and how long it shines. The planet then has to play with whatever tools it has: a magnetic field to deflect charged particles, an atmosphere thick enough to absorb radiation, and climate systems that can move heat from day to night. Here is where spectral energy distribution comes in. It should be noted that a red dwarf like Teegarden star emits most of its light in the infrared, with very little in the bright, visible wavelengths our eyes prefer. A planet in its Goldilocks zone receives energy, but in a different color balance than Earth. Dark surfaces may absorb this infrared more efficiently. Ice and clouds may reflect it differently. Even photosynthesis would have to adapt, perhaps using pigments tuned to deep red and infrared instead of our familiar green. There is a deeper, almost philosophical difficulty here. Red dwarfs can live for trillions of years. Optimistically speaking, that is an enormous window for life to arise and evolve. But while their lifetimes are generous, their behavior can be vicious, especially when they are young. So is that long cosmic lifespan a gift, or does the early violence permanently sterilize many worlds? So it's time to find out the truth about Teegarden's star itself. Before we imagine oceans, forests, or alien astronomers on Teegarden star B, we have to ask a simpler question. What kind of sun are they standing under, and how does it treat its planets? Inside an ultra-cool dwarf, Teegarden star up close. So what kind of sun would Teegarden star B rise under, if it even has a sunrise at all? Evaluating that means we have to zoom in on the star itself, because in the hunt for alien life, the star is half the story. Teegarden star is what astronomers call an ultra-cool red dwarf. Picture something only slightly larger than Jupiter in diameter, but more than 70 times Jupiter's mass, squeezed into that volume. This means it is less than 10% the mass of the Sun, and only about 8% of the Sun's size. In terms of brightness, it is astonishingly faint, roughly 1,000th the Sun's luminosity. If you swapped our Sun for Teegarden star, Earth would instantly plunge into a deep, permanent ice age. But while it is tiny and dim, it is also incredibly long-lived. Because it burns its hydrogen fuel so slowly, Teegarden star is expected to shine not for 10 billion years like the Sun, but for hundreds of billions, potentially even a trillion years or more. It should be noted that the entire universe is only about 13.8 billion years old, so this star will still be around long after the Milky Way's current shape has dissolved. This means any habitable planet in this system could, in principle, have a window for life far longer than Earth has ever had. There is a catch. Red dwarfs, especially when young, are notorious troublemakers. Their strong magnetic fields can twist and snap, releasing powerful flares and bursts of high-energy radiation. For a planet in the Goldilocks zone, which orbits very close in, that radiation can be intense. Over hundreds of millions of years, repeated flares and stellar winds can erode an atmosphere, strip away water, and sterilize the surface. So let's begin by asking, is Teegarden star one of the quiet ones, or one of the monsters? The data we have are limited, but suggestive. Teegarden star is old, probably more than 8 billion years, and its spectrum shows relatively weak signs of the hot churning chromospheres seen in very active red dwarfs. Its light curve, how its brightness changes over time, does not show dramatic, frequent outbursts. Optimistically speaking, it appears less feisty than extreme flare stars like Proxima Centauri, though not as well characterized as TRAPPIST-1, where we have years of precise monitoring.
So it's time to find out the truth about what this means for Teegarden star B. A long-lived but violently active star could have blasted away its planet's atmosphere early, leaving a cold, airless rock locked in eternal day and night. A somewhat calmer star, by contrast, might allow a thick atmosphere and maybe oceans to survive for billions of years. The puzzle is that from our current vantage point, we see just enough quiet to be hopeful, but not enough detail to be certain. Is Teegarden star a gentle ember, or a sleeping dragon that once scorched its worlds? To answer that, we have to leave the star's surface and drop down to the orbit of Teegarden star B itself, where conditions become truly alien. A rarely gentle red dwarf? Why, Teegarden might be different. If Teegarden star once behaved like a dragon, could it already be past its fire-breathing phase? In the hunt for alien life, that single detail might decide whether Teegarden star B is a living world or a stripped rock. Teegarden star is not a young object just lighting up. It should be noted that stellar models and its slow rotation suggest an age of at least 8 billion years, possibly older than our Sun. For a red dwarf, that is middle-aged to elderly, and elderly red dwarfs tend to calm down. Their magnetic fields weaken, their star spots fade, and the violent flares that dominate their youth become less frequent and less energetic. So, what do the data actually say? Astronomers have watched Teegarden star with ground-based telescopes and space missions like TESS, looking for sudden, bright spikes that would betray huge flares. They do see variability and a few modest events, but nothing like the relentless storms we associate with the worst flare stars. No superflare has yet been clearly recorded. This means, at least during the monitoring windows we have, Teegarden star behaves more like a quietly simmering ember than a strobe light. To understand why that matters, we can compare it to Proxima Centauri. Proxima is also a small red dwarf, but it flares furiously, throwing out blasts of X-rays and ultraviolet light hundreds of times brighter than its usual output. Some campaigns have seen large flares multiple times per week. Teegarden star, by contrast, shows a much lower flare rate and more modest amplitudes in the optical band, with estimated high energy output over time likely an order of magnitude or more below Proxima's. Optimistically speaking, that is a huge difference for any planet clinging to an atmosphere. Why? Because every major flare is a direct attack on a planet's sky. High-energy photons and charged particles slam into the upper atmosphere, heating it, breaking molecules apart, and driving gas out into space. Around an active red dwarf, this erosion can, over billions of years, strip away water and air, especially on small, Earth-like planets huddled close in the Goldilocks zone. A quieter star gives the atmosphere a fighting chance to recover between hits, to rebuild ozone layers, to keep oceans from boiling off into space. So if we had to pick a red dwarf in our local neighborhood and say, place an Earth-like planet here and hope for the best, an older, slower rotating, relatively calm object like Teegarden star would be near the top of the list. In the hunt for alien life, that makes this system unusually promising. So it's time to find out the truth about the trade-off. A gentle star helps, but Teegarden star still clings very close to its dim sun, almost certainly locked with one face in eternal day and the other in endless night. Even under a quieter red dwarf, that kind of orbit sets the stage for some extreme and potentially hostile climates. How we stumbled on a hidden neighbor, the discovery of Teegarden star. So if Teegarden star orbits so close, why did we only recently learn that its star even exists? For something just 12.5 light years away, you would think it would have been on our maps for a long time. It should be noted that Teegarden star itself was only announced in 2003. Bernard Teegarden and his colleagues were not pointing a telescope at some obvious bright target. Instead, they were digging through archival sky survey data, frame by frame, looking for tiny changes over time. On those plates, most stars sit still, but one faint reddish point was sliding noticeably against the background. This motion is what astronomers call proper motion, the slow drift of a star across the sky as it moves through the galaxy. Nearby stars tend to show large proper motions because their true space motion translates into a bigger apparent shift. But while bright neighbors like Barnard's star were found early, a very dim red dwarf can hide in plain sight. It is there on every image, but so faint that our catalogs overlook it. Teegardens' team realized that this fast mover was special. By measuring how quickly its position changed from year to year, they could estimate that it had to be quite close. Follow-up observations with larger telescopes then refined the picture. Its spectrum revealed an ultra-cool red dwarf, far cooler and smaller than the Sun, glowing mostly in deep red and infrared. Parallax measurements, comparing its apparent position from different points in Earth's orbit, pinned down the distance to around 12.5 light-years. This means that, at the time of discovery, we had an almost new neighbor in the cosmic sense, hiding just beyond our doorstep. In the hunt for alien life, that is a sobering reminder. If we can miss an entire star so close by, how many more faint red dwarfs, each with their own planetary system, are still waiting in the data? Optimistically speaking, every overlooked red dwarf could be another chance at an Earth-like world in a quiet Goldilocks zone. Teegarden's star joined the growing family of nearby ultra-cool dwarfs like TRAPPIST-1 and Proxima Centauri, but with its own personality, tiny, dim, apparently old, and relatively calm. As astronomers measured its mass, temperature, and luminosity, a new question naturally followed. If this small star is so close and so stable, could it host planets whose orbits and atmospheres we might actually study?
So, let's begin the next chapter. Once the star was on the books, the search shifted from, "What is this object?" to, "What is circling it?" And that is where Teegarden Star B finally enters the story. From wobbles to worlds, how Teegarden Star B emerged from the data. Once astronomers knew Teegarden Star was there, the next step was clear. We had to watch it closely. In the hunt for alien life, a quiet, nearby red dwarf is an irresistible target, and one of the main tools for this job is a spectrograph called Carmenes. Carmenes is mounted on the 3.5-meter telescope at Calar Alto Observatory in Spain, and it is purpose-built to listen for stellar heartbeats. It breaks the star's light into thousands of spectral lines and tracks them with absurd precision, looking for tiny shifts in color. Other instruments, like HARPS and HARPS-N, do something similar, but Carmenes is especially tuned to red dwarfs, which shine mostly in the infrared. So how does this actually reveal a planet? We usually picture a planet simply orbiting a star. But while that is roughly true, the deeper reality is more balanced. Both the star and the planet orbit a common center of mass. This means the star itself moves in a tiny, repeating wobble. When the star moves toward us, its spectral lines shift slightly bluer. When it moves away, they shift redder. Detecting that pattern is what we call the radial velocity method. For Teegarden's star, those motions are only a few meters per second, walking speed on Earth. Yet, with years of careful observations, Carmenes could measure them. It should be noted that this is at the edge of what our current technology can do, especially for such a faint, cool star. By 2019, the Carmenes team had enough data to see something remarkable. They found periodic signals in the star's motion, one repeating every 4.9 days, another every 11.4 days. The simplest explanation? Two planets, now called Teegarden's Star B and Teegarden's Star C, each tugging on the star in its own rhythm.
From the size of the wobble, astronomers estimated minimum masses very close to Earth's. These were not gas giants. These were Earth-like worlds in a compact system, each completing an orbit in less than 2 weeks. Optimistically speaking, that is exactly the kind of configuration we hope for when we talk about a nearby Goldilocks zone. But were these signals real planets, or just noise from the star's own magnetic activity? So it's time to find out the truth. The team checked whether the 4.9 and 11.4 day cycles lined up with known activity patterns, star spots, or flares. They did not. The signals stayed stable in period, phase, and amplitude over multiple observing seasons, even as the star's surface behavior changed. This means astronomers are confident. These wobbles are worlds. And the key result is striking. Teegarden star B, the inner planet, sits in the habitable zone and receives nearly Earth-like energy from its dim red dwarf sun. So what does that actually feel like on the surface of such a world? And could its atmosphere truly support life? That is where our journey turns from numbers on a graph to the weather on an alien sky. So, habitable or not? The question we still can't answer cleanly. So if Teegarden star B looks this good on paper, does that actually make it a place where life could exist? We have a nearby, ultra-cool red dwarf star that seems relatively quiet, at least compared to its more violent cousins. We have an Earth-mass planet in a tight 4.9 day orbit, sitting in the Goldilocks zone and bathing in almost exactly the same total energy that Earth receives from the Sun. And from its mass and the nature of the system, we have strong reasons to think this is a rocky world, not a puffy gas mini Neptune. This sounds almost too perfect. In the hunt for alien life, finding a small, dense planet with Earth-like irradiation around a calm, long-lived star is about as good as our wish list gets. So let's begin with the obvious question. Does that mean Teegarden star B is habitable or even inhabited? This is where we have to slow down, because all of those impressive numbers we just listed still leave out the crucial layers that actually decide whether a world can host oceans, climates, and biology. We do not yet know if Teegarden star B has an atmosphere at all. If it does, we do not know its thickness, its chemistry, or whether it includes greenhouse gases like carbon dioxide or water vapor. We do not know how strong the planet's magnetic field might be, or how much water it started with, or how much it may have already lost to space. So it's time to find out the truth about how uncertain we still are. When you see headlines saying, Earth-like planet found just 12.5 light-years away, it sounds as if we have already checked every box. But while those headlines are great for capturing attention, the scientific reality is much more fragile. Right now, our climate models for Teegarden star B are essentially educated guesses, run on computers with many different assumptions about air pressure, clouds, and circulation patterns on a tidally locked world. This means 2 different teams can plug 2 different atmospheric scenarios into their models and get wildly different results. One version with a temperate, ocean-bearing dayside, and another with a frozen, airless rock. Which one is real? Without direct atmospheric data, we simply cannot say. It should be noted that our optimism about red dwarf planets has already taken some hits. TRAPPIST-1 showed us worlds that are probably stripped or steam-bathed. Proxima b orbits a star that flares so intensely it may erode any atmosphere over billions of years. Given those lessons, should we really be quick to call anything Earth 2.0 just because it orbits in a red dwarf's habitable zone? Optimistically speaking, Teegarden star looks calmer and older than many of these examples. That could mean its planets had a gentler radiation history. But even there, we are working from indirect indicators, not from weather reports on the surface. So where does that leave us? At a tantalizing crossroads. We have a planet that checks the big, simple boxes. Right mass, right orbit, right energy. But the fine print is missing. In the next sections, we will dive into that fine print. How climate physics behaves under a dim red sun. How easily atmospheres can escape. And what tidal locking really does to a world's habitability. How far can we push the question of Teegarden's star B with the science we have today, before the telescopes of tomorrow finally look directly at this alien sky? How sure are we, really, the limits of our data on Teegarden's star B? So how sure are we about any of this, really? When we talk about Teegarden's star B as a potentially habitable world, are we standing on solid scientific ground, or are we still mostly guessing in the dark? In the hunt for alien life, Teegarden's star B is one of those planets that sounds almost too perfect at first glance. What do we actually know with reasonable confidence? We know its orbit very well. It circles its ultra-cool red dwarf in about 4.9 Earth days. That tight orbit, combined with the star's dim glow, tells us the planet receives roughly Earth-like stellar energy. This means, in terms of raw light and heat, it really could sit in a Goldilocks zone. We also know its minimum mass from the wobble it induces in its star. It is extremely close to Earth's mass, which strongly suggests a rocky, Earth-like planet rather than a gas mini-Neptune. Given its distance from the star and the system's old age, climate models almost all converge on one key point. Teegarden's star B is probably tidally locked, with one face in eternal day and the other in endless night. But while that sounds impressively specific, the list of what we do not know is even longer. We do not know the exact radius of the planet, so we cannot calculate its true density. Without that, its detailed composition is uncertain. Is it Earth-like rock and iron, water-rich, or something in between? We do not know if it has an atmosphere at all, let alone how thick it might be, or what gases dominate it. Surface pressure, cloud cover, and whether there is liquid water anywhere on or beneath the surface all remain completely open questions. Here is the real bottleneck. We have not seen Teegarden's star B transit its star. It should be noted that a transit is our golden ticket. If the planet passed directly in front of the star, from our point of view, we could measure its radius precisely. More than that, we could use transmission spectroscopy, letting starlight filter through any atmosphere to sniff out molecules like water vapor, carbon dioxide, or methane. Without a transit, those tools are simply off the table for now. So how do scientists proceed? They run climate models as scenarios, not as predictions. One setup assumes no atmosphere at all. Another assumes an Earth-like mix of nitrogen, water, and CO2. Others explore Venus-like thick CO2 blankets or high-pressure water worlds. Each simulation asks, under this set of assumptions, could any region of the planet be habitable? The goal is not to declare a single truth, but to bracket what is physically plausible. Pattern interrupt. What if everything we have just said turns out to be wrong? Optimistically speaking, future observations could change the picture overnight. If a transit is finally detected, JWST and its successors could probe the planet's air directly. If next-generation giant telescopes manage to image the system, we might even measure temperature contrasts between the day and night sides. So it's time to find out the truth in the coming decades. Teegarden's star B may either rise as one of the best Earth-like candidates in the nearby universe, or quietly leave the stage as just another sterile rock. And to understand which way the story might go, we first need to explore how climates behave on tidally locked worlds under a dim red sun. A system on fast forward, the big picture habitability of Teegarden's worlds. Climates are one thing, but what happens when we zoom out and look at the entire planetary system Teegarden's star has built around itself? In the hunt for alien life, these big picture patterns matter. They tell us whether we are looking at a chaotic cosmic accident or at a carefully arranged clockwork of worlds that could stay habitable for billions of years. Teegarden's star is tiny, but its planetary system is anything but empty. As far as we can tell, it hosts at least 2 Earth-mass planets, B and C, both on incredibly tight, short-period orbits. Their entire architecture is compact. Everything is packed well inside the distance of Mercury's orbit in our own system. This means that if you could look down from above, you would see 2 small, dark marbles racing around a faint red ember, tracing out years that last only a few days. It should be noted that this arrangement immediately reminds us of another famous red dwarf, TRAPPIST-1. Both stars are ultra-cool. Both are low mass, and both are orbited by close-in rocky planets that are probably tidally locked. But while TRAPPIST-1's 7 planets form a delicate resonant chain, each orbit locked in step with its neighbors, Teegarden's system looks simpler and more spread out. We only know of B and C so far, and their orbits are not obviously resonant based on current data. There is another key difference. TRAPPIST-1's planets were discovered by watching them transit, repeatedly dimming the star's light. Teegarden's worlds, on the other hand, were teased out through tiny gravitational wobbles in the star's motion. This means we have exquisite timing and size information for TRAPPIST-1, but for Teegarden's star B and C, we instead know their minimum masses and orbital periods, and we strongly suspect a whole family of compact, Earth-like worlds could still be hiding. So where does the Goldilocks zone fall in this fast-forward system? Teegarden's star B appears to sit in the inner part of the habitable zone, receiving roughly Earth-like energy, perhaps a bit more. Teegarden's star C likely lies slightly farther out, on the cooler, dimmer side. This immediately hints at a natural climate gradient. B might lean toward warm oceans or even borderline greenhouse conditions, while C could favor cooler, cloudier skies, maybe even icy caps creeping toward the terminator. Optimistically speaking, that diversity is exactly what we want. If any red dwarf system can host life, nearby, quiet systems with multiple Earth-mass planets in or near the habitable zone are among our best bets. Teegarden's star seems old and relatively stable, meaning any atmospheres that survived the star's early tantrums could now enjoy hundreds of billions of years of calm. So it's time to find out the truth at a more human scale. What would it actually feel like to stand on Teegarden's star B, under a dim red sun that never moves, on a world where a year is less than a work week? In the next section, we will slow that racing orbit down and walk through a single day in the life on this strange, tightly bound planet. Locked to its star, the strange geometry of a tidally locked world. So if the day on Teegarden's star B is less than a work week, why does the star in the sky never move? To answer that, we have to twist our sense of what a day even is. On Earth, a day is simple. We spin. The ground turns under the sun, and light and darkness chase each other around the planet. But while Earth rotates freely, some worlds get locked into a strange gravitational dance. This means the same side always faces their star. Our own moon does this with Earth. We only ever see one lunar face, because its spin and its orbit are perfectly synchronized. Teegarden's star B almost certainly lives under that same rule. As it races around its cool red dwarf in just 4.9 days, it keeps one hemisphere staring straight into the red light and the other plunged into endless night. There is no sunrise, no sunset, just a sky frozen in place for billions of orbits. So let's begin to redraw the map of this planet. Instead of time zones, think heat zones. First, directly under the fixed red sun, there is the substellar point, a blazing bullseye where starlight falls straight down, all day, every day, forever. Around the back, on the exact opposite side,
lies the anti-stellar point, a frozen abyss that never sees its star, lit only by distant galaxies. Between those extremes wraps a narrow twilight ring, the terminator. Here, the star forever hovers on the horizon, neither fully risen nor truly set. Imagine walking around the planet along that circle and never leaving a world of permanent sunset. In the hunt for alien life, this strange ring may be the most precious real estate.
But what does this geometry do to climate? With so much energy focused on one face, the day side could heat up until rock glows, and oceans, if they exist, steam furiously. The night side, cut off from direct light, might cool until the atmosphere itself starts to freeze and fall as exotic snow. It should be noted that if too much gas gets trapped as ice in the dark, the entire atmosphere could collapse. So what saves it? Winds, and if Teegarden star B has oceans, powerful currents. Picture a giant heat engine, hot air rising under the substellar point, then flowing outward at high altitude toward the night side, cooling, sinking, and sweeping back along the surface. Optimistically speaking, this global conveyor belt could smear out the temperature difference, keeping the night side just warm enough and the day side just cool enough for liquid water. Some simulations even show a sweet spot forming right on that twilight ring where temperatures hover near Earth-like values. So it's time to find out the truth. On Teegarden star B is the most comfortable place to live, not under the noon sun, but in a perpetual band of evening wrapped around the planet. In the next section, we will step into that eternal sunset and ask what it would actually feel like to stand there, breathe there, and maybe, one day, live there. 3 faces of Teegarden star B: bare rock, Earth twin, or mini Venus. So if we step into that eternal sunset, what kind of world are we actually standing on? In the hunt for alien life, Teegarden star B might wear 3 very different faces, and each one would feel utterly different to a human explorer. First, imagine the bare rock world. No real atmosphere, just a whisper of gas hugging the surface. The red dwarf star hangs motionless in the sky, a deep ember blazing in infrared. On the day side, unfiltered radiation beats down, driving temperatures far above boiling. The sky is almost black blue, with no haze to scatter the light, and shadows are razor sharp. You would need a spacesuit, not for cold, but to keep from being cooked. Cross the line into night and everything flips. Without air to move heat, the temperature plunges toward cryogenic values. Any remaining gas could literally freeze out onto the surface as frost. You would see a stark, airless desert on one side and a frozen, lightless wasteland on the other, with no clouds, no oceans, no ice caps in the Earth-like sense, just rock and vacuum. But while that is the harshest option, there is a second, far more hopeful face. So let's begin with an Earth-like atmosphere. Something with moderate pressure and a mix of nitrogen, oxygen, and perhaps some CO2 and water vapor. This means winds can carry heat from the day side into the night, smoothing out the extremes. On the day hemisphere, the sky might glow a deep copper or muted purple because the star's light is redder than our sun's. Clouds could cluster under the substellar point, forming a bright, reflective shield that keeps the surface surprisingly temperate. Walk into the Terminator, and you might feel a cool, steady breeze as air flows from warm to cold, and see a permanent band of twilight with rivers or even an ocean glinting under a low, red sun. Ice caps could cling to the far night side, hidden under starlit clouds. Optimistically speaking, this is the truly habitable version. Then there is the third face, the mini Venus. A thick, CO2-rich atmosphere, maybe dozens of times Earth's surface pressure, traps heat with a brutal greenhouse effect. The day side becomes a world of shrouded brightness.
You never see the star directly. Only a uniform, yellow-orange glow filtered through permanent clouds. The temperature at the surface could soar to hundreds of degrees. Any human would be crushed and baked without extreme protection. Winds in the upper atmosphere might howl at hundreds of kilometers per hour, but down below, you would see only a hazy, featureless plain of rock. No blue oceans, no visible ice, just a pressure cooker. So which face does Teegarden's star, the actually show? It should be noted that this depends heavily on its starting conditions. How much water did the planet form with? Did the young star blast away its early atmosphere with intense flares, as many red dwarfs do? Or did it calm down quickly enough for oceans to condense? Early loss of water could push it toward the bare rock or mini-Venus paths, while a gentler youth might preserve an Earth-like climate attractor. Right now, our data only give us mass, orbit, and rough energy input, not the decisive details. Pattern interrupt. Imagine rewinding the entire system and rolling the dice again. The same planet in the same Goldilocks zone could end up in any of these three states, depending on subtle differences in history. So it's time to find out the truth. In the next section, we will look at how future telescopes might finally tell these faces apart and reveal whether that eternal sunset is hellish, frozen, or quietly, astonishingly habitable. When the star tries to kill you, flares, winds, and atmospheric escape. So if the same world in the same Goldilocks zone can end up hellish, frozen, or quietly Earth-like, what decides its fate? A big part of the answer is brutal, the star itself, and the invisible storm it throws at its planets. Teegarden star is a tiny, ultra-cool red dwarf, but small does not mean gentle. Red dwarfs are famous for violent stellar flares and coronal mass ejections, explosive outbursts where magnetic fields snap and hurl energy into space. In seconds, the star can flood its system with X-rays and ultraviolet light. This radiation slams into a planet's upper atmosphere, ionizing atoms, heating the gas, and sometimes blasting it outward into space. In the hunt for alien life, these flares can be both sculptors and executioners. When an atmosphere is heated from above, it swells. If the gas at the very top gets hot enough, individual molecules can reach escape velocity and drift off forever. This is thermal escape, and for a planet close to its star, it never really stops. But while simple heating is one route, it should be noted that it is not the only one. High-energy particles in the stellar wind can knock atmospheric atoms away like billiard balls, a process called sputtering. At the same time, a dense, fast, stellar wind can literally strip the upper layers through sheer pressure, eroding the shield that makes a surface habitable. Close-in planets like Teegarden's star B are on the front line of this battle. It orbits in less than 5 days, bathing in a constant drizzle of charged particles and radiation. We have already seen what this might mean in other systems. Around TRAPPIST-1, models suggest that the inner planets could have lost oceans worth of water to flares and winds. Proxima b, circling an even more active red dwarf, may have had its atmosphere severely eroded over billions of years. So it's time to find out the truth. Does Teegarden's apparently quieter nature really change the outcome? Optimistically speaking, Teegarden's star seems less active than Proxima, or the most extreme flare stars. This means the average assault on Teegarden's star B might be milder, giving any atmosphere a better chance to survive. And this is where the planet itself can fight back. A strong planetary magnetic field can deflect a large fraction of the charged particles, carving out a protective bubble. An Earth-mass rocky planet, cooling slowly over billions of years, could plausibly run a molten iron core and a dynamo, just as Earth does. But while that sounds reassuring, we do not yet know if Teegarden's star B actually has such a field, or whether early, more intense flaring already stripped away most of its air before the star calmed down.
Has it spent billions of years bleeding its atmosphere into space, or billions of years settling into a stable, protected cocoon of air and water? In the next part, we will see how future data might finally reveal whether this quiet ember of a star has preserved a living world, or left behind a bare, irradiated rock. Could the air collapse? The night side freeze-out problem. So if Teegarden star B did manage to hang on to an atmosphere, could it still lose it in a completely different way? Not to space this time, but to its own frozen night side, one molecule at a time. On a tidally locked planet, there is no sunrise or sunset. One hemisphere stares at the red dwarf forever. The other is trapped in endless darkness. That dark hemisphere can become so cold that the air itself starts to snow out. This means gases like carbon dioxide, and in extreme cases even nitrogen, can condense, freeze onto the surface, and effectively collapse the atmosphere onto the night side. Why is that so dangerous for habitability? Because once enough gas freezes out, the global pressure drops. Lower pressure means less greenhouse warming, which makes the night side even colder, which freezes out even more gas. It should be noted that this is a runaway feedback loop. Left unchecked, you end up with a thin, Mars-like envelope of air and vast glaciers of what used to be your atmosphere, locked in permanent shadow. Climate models of tidally locked worlds around red dwarf stars show there is a way out. If the planet has a sufficiently thick atmosphere, or large oceans that can store and transport heat, winds and currents can carry enough energy into the dark hemisphere to keep it above the condensation point of key gases. Optimistically speaking, a surface pressure of around 1 bar of mixed nitrogen and carbon dioxide with some water vapor can keep many modeled planets in the Goldilocks zone safely away from collapse. So where does Teegarden star B sit in this picture? It receives roughly Earth-like energy from its tiny star, but probably spreads that energy very unevenly across its face. In the hunt for alien life, that uneven heating is both a challenge and an opportunity. Models for similar planets suggest that if Teegarden star B has at least a few tenths of a bar of atmosphere, dominated by nitrogen with a modest amount of carbon dioxide, strong winds could keep the night side cold but stable, maybe 100 to 150 degrees Celsius below freezing, yet still above the point where nitrogen would start to liquefy or freeze. Imagine walking from the bright day side toward the Terminator, that eternal twilight ring. At first, the ground is wet, maybe muddy, with liquid water pooling in low areas. As you move deeper into the dim zone, the air cools rapidly. Your breath steams. Frost begins to crust the rocks, and patches of permanent ice fill the shadows. Cross fully into the night side, and the sky is a black dome, lit only by the red halo of the star over the distant horizon. Here, carbon dioxide frost might sparkle under starlight, and every exhalation would instantly freeze. If the atmosphere is thick and circulating, that brutal night is still just cold, not lethal to the entire planet. The air remains global. Pressure stays high enough for liquid water in the twilight band, and the Terminator could host a narrow but truly habitable strip. But if Teegarden star B allowed its air to collapse, surface water would vanish, chemistry would grind to a halt, and life would be forced underground or into the deep ocean, if any ocean survived at all. So it's time to find out the truth. Is Teegarden's star B wrapped in a robust, heat-shuttling cocoon of air, or is its night side a vast, atmospheric graveyard? In the next section, we will see how future observations might finally let us measure that invisible balance between day and night. A day in the life on the Terminator, living in eternal sunset. To really feel what is at stake in that invisible balance, we have to stop thinking like distant observers and imagine that we live there. So let's begin at the only place on Teegarden's star B where an Earth-like biology might be most comfortable, the thin twilight ring along the Terminator.
Above you, the sky never brightens into day and never fades into true night. The ultra-cool red dwarf star hangs forever just above the horizon, a dull ember smeared by the thick atmosphere, casting long, razor-sharp shadows that never move. The light would feel strange to us. Instead of white sunlight, everything is washed in deep reds and dim oranges, as if the entire planet is trapped in an endless sunset. Blue and green pigments reflect poorly here, so forests, if they exist, might look almost black or a dark, metallic purple, tuned to drink in the infrared glow of their star. In the hunt for alien life, this kind of adaptation is not a luxury, it is a requirement. Climate here is all about contrast. On the day side, heat piles up under the fixed glare. On the night side, energy bleeds away into space. This means the Terminator becomes a permanent atmospheric racetrack. High above you, powerful winds roar from the hot hemisphere toward the cold, like a global jet stream wrapped around the planet. Near the surface, cooler, denser air slides back along the ground, closing the loop. Walking toward the star, you would feel a constant headwind, a steady reminder of that tug of war between fire and ice. It should be noted that these winds might reach hundreds of kilometers per hour at altitude, yet be tamed near the ground by terrain, vegetation, or even engineered windbreaks if a civilization exists.
Geography would decide where life clusters. On the night side slopes, vast ice fields could creep forward, their edges melting as they cross into the twilight. Meltwater might pool into long, curving lakes that trace the Terminator, or collect in basins to form narrow, ring-shaped seas where temperatures hover near the freezing point, but rarely stray far. Rocky highlands facing the star would catch the last, weakest light, becoming precious real estate for photosynthetic ecosystems. But how do you tell time on a planet where the star never rises or sets? Instead of morning and evening, people might speak of upwind and downwind, or starward and shadowward. Daily routines could be anchored not to a changing sky, but to subtle cycles in wind strength, cloud patterns, or even the rhythmic flexing of the planet's magnetic environment. Pattern interrupt. Imagine never teaching a child what a sunrise is. Optimistically speaking, a culture here might still discover the concept of a day by watching other worlds in their system transit their star, or by carefully tracking the faint wobble of Teegarden star itself. So it's time to find out the truth. If intelligent life evolved under this single, unchanging sky, would they even have a word for day at all? Or would their entire history unfold in one eternal crimson dusk? Could life adapt to a red sun? Infrared photosynthesis and alien biology. If the sky never changes, could life itself change the rules of biology to match it? On Teegarden star B, the answer may depend on whether alien organisms can learn to live under a red sun that barely shines invisible light at all. Evaluating a star system for compatibility with life is tricky. On Earth, almost everything ultimately traces back to photosynthesis, powered by our bright yellow-white star. But Teegarden star is an ultra-cool red dwarf, radiating most of its energy in the infrared. This means the photons bathing Teegarden star B are less energetic, redder, and more like gentle warmth than sharp blue-white sunlight. In the hunt for alien life, that completely reshapes the playing field. On our own planet, plants show a sharp red edge in the reflectance spectrum, absorbing visible red light for photosynthesis and reflecting most near-infrared. Theoretical work suggests that around a red dwarf, that edge could shift. Pigments might evolve to grab those longer wavelengths efficiently, pushing photosynthesis deeper into the infrared. So let's begin to imagine forests of very dark, almost black vegetation, tuned to capture every stray photon from that dim ember in the sky. But while we say forests, the actual ecosystems might look very different. Under a cooler star and a perpetual twilight, tall trees might be rare or impossible. Instead, we could see low, mat-like growths hugging the ground to conserve heat, or thick, rubbery fronds sprawled across rocks, maximizing surface area. It should be noted that on Earth, microbial mats already dominate extreme environments, from hot springs to Antarctic lakes. On Teegarden star B, similar mats could carpet shorelines and shallow seas, quietly harvesting infrared light. Now picture an ocean on the night side or beneath seasonal ice. Dim, red-tinged light filters through water and maybe a translucent ice shell, just enough for exotic pigments to work slowly, accumulating energy over long periods. In such a world, photosynthesis might be sluggish but steady, supporting simple food webs of grazers and predators adapted to the eternal dusk. However, not all life needs starlight. Around our own deep-sea vents, chemosynthetic microbes thrive on chemical energy from the planet's interior, completely independent of the sun. Teegarden star B could host similar communities, powered by geothermal heat, tidal flexing from its tight orbit, and hydrothermal systems on the sea floor. This means entire biospheres might exist that barely notice what the star is doing overhead. And if biology is built for infrared, its fingerprints may fool us. A shifted vegetation red edge would alter the planet's reflectance spectrum. Unfamiliar pigment chemistry could produce colors and patterns our current models do not expect. Atmospheric gases like oxygen, methane, or exotic sulfur compounds might appear in different proportions or time variations. Optimistically speaking, such worlds could be rich in life, yet our telescopes might misread them as barren.
So it's time to find out the truth. When we finally point our most powerful instruments at Teegarden star B, will we even recognize alien biology shaped by a red sun? Or will its living signal hide in plain sight, buried inside spectra we do not yet know how to interpret? What would aliens on Teegarden star B see when they look at us? If alien biology might hide inside spectra we barely understand, we have to ask an even stranger question. What if someone out there is already trying to read ours? What would Earth look like through the eyes of astronomers on Teegarden's star B? So let's begin on a dark plateau under a red sky. Above them, Teegarden's star glows like a dull ember, but their telescopes are not pointed at their own star tonight. They're turned toward a faint yellow point 12.5 light-years away in their sky, our sun. In the hunt for alien life, this is their promising target, just as their planet is one of ours. How would they even notice us? First, they could measure tiny wobbles in their star maps, watching the sun shift back and forth under the pull of its planets. With enough patience, the radial velocity tug of a small, rocky world every 365 days would stand out from Jupiter's heavier, slower influence. A repeating signal, a year-long orbit, a world at roughly 1 astronomical unit. But while radial velocity hints at a planet, it does not show them a silhouette. If their line of sight happens to align just right with the plane of our solar system, they get far luckier. Every year, the Earth would briefly cross the sun's face, dimming that yellow star by less than 1/100%. To them, this transit would be what our telescopes dream about. A clean, periodic dip in light from a bright, stable star. From that pattern alone, they could infer our orbital period and distance, and combine the transit depth with the sun's size to estimate Earth's radius. The radial velocity wobble then adds mass. This means they can calculate our density and conclude that Earth is a rocky, Earth-like planet, not a gas giant in disguise. It should be noted that during each transit, a tiny fraction of starlight would filter through our atmosphere. By spreading that light into a spectrum, they could search for fingerprints of gases, oxygen, ozone, water vapor, maybe even methane. They would not see continents or oceans, but they might see the spectral hints of clouds and a complex layered atmosphere clinging to a temperate world in the Goldilocks zone. To them, Earth would be a maybe, a potentially habitable dot with intriguing chemistry, but no direct proof of life. Optimistically speaking, they might argue in their own observatories that such a planet is too interesting to ignore. And here is the symmetry. Everything they can infer about us from a few delicate dips in starlight is almost exactly what we can infer about Teegarden star B: a mass, a radius, an orbit, an atmosphere, and a vast ocean of uncertainty. So it's time to find out the truth from both directions. With tools this limited, yet powerful, how do we turn sparse data points into living, breathing worlds without fooling ourselves? If life exists there, how would we know? Biosignatures on a red dwarf world. So if there is life on Teegarden star B, how would we ever know from 12.5 light years away? In the hunt for alien life, we do not get close-up photographs. We get spectra, thin rainbows of starlight filtered through a distant atmosphere, whispering what kinds of molecules might be there. So let's begin with the classics. On Earth, our atmosphere is wildly out of chemical balance. Oxygen is incredibly reactive. It should vanish quickly as it rusts rocks and reacts with volcanic gases. Methane should be destroyed by sunlight in just a few years. Yet we have both, side by side, in a persistent disequilibrium. This means something is constantly replenishing them. Here, that something is life. For Teegarden star B, we would search for similar atmospheric fingerprints, oxygen paired with methane, or perhaps nitrous oxide, a gas produced by microbes on our own planet. These molecules are hard to maintain without a steady biological source. If we saw strong, stable signals of them in the atmosphere of an Earth-like planet, it would be very hard to explain away. But while the recipe is familiar, the kitchen is very different. Teegarden star is an ultra-cool red dwarf, shining mostly in infrared rather than visible light. Its spectrum reshapes atmospheric chemistry. With less high-energy ultraviolet, ozone might form less efficiently, changing how deeply UV penetrates and how fast methane is broken down. Flares from the star can briefly flood the system with radiation, driving bursts of photochemistry that do not look like anything we see on Earth today. It should be noted that this complicates our models. The same mix of gases that screams biology around a sun-like star might be ambiguous around a red dwarf. A planet could build up oxygen abiotically if intense early flares stripped away oceans, leaving behind oxygen-rich air with no life at all. Surface clues are just as tricky. On Earth, green plants reflect strongly in the near-infrared, producing the so-called vegetation red edge. Alien astronomers could, in principle, see this sharp change in reflectivity as our continents rotate in and out of view. But around a dim red dwarf, photosynthetic life might adapt pigments tuned to the star's infrared output. The red edge could shift to much longer wavelengths, maybe deep into the infrared, where our current telescopes struggle. And what about false negatives? A world covered by a global ocean, or by thick clouds, might host thriving ecosystems that barely alter the atmosphere at all. Or Teegarden star B could be in a quiet, pre-oxygen stage, rich in microbes, but spectrally almost invisible. Optimistically speaking, Teegarden star B is a prime theoretical target to test all of this. But actually confirming life there would push our instruments and our imagination right to their limits. So how do we design observations and future telescopes to tease out such delicate signals without being fooled by a dead but active planet? That is where the next part of our journey leads. What JWST, ELT, and future telescopes can and can't do for Teegarden star B. So what can our current telescopes actually do with a tiny Earth mass planet 12.5 light years away that doesn't even seem to pass in front of its star? In the hunt for alien life, this is where the romance of discovery slams into the hard wall of instrumental limits. We often imagine the James Webb Space Telescope as an all-seeing eye, able to read the chemistry of any distant atmosphere. But while JWST is incredibly powerful, it has a very specific superpower. It's best when a planet transits, briefly dimming its star so we can see starlight filtered through the atmosphere. Teegarden star B, as far as we know, does not transit. This means no straightforward transmission spectrum, no neat infrared fingerprint of gases like CO2 or methane. So is JWST useless here? Not at all. It should be noted that Webb can still measure Teegarden star itself with exquisite precision. By nailing down the star's temperature, radius, and activity, we refine how much energy Teegarden star B actually receives and how stable its environment might be. JWST can also stare for long periods, searching for tiny, rare transits that earlier surveys might have missed. If we got lucky and found even a grazing transit, the entire game would change overnight. But while JWST works from space, an entirely different class of instruments is rising from the ground. Enter the extremely large telescope in Chile, with a mirror 39 meters across. So, let's begin to imagine what that means. With adaptive optics sharpening its view and ultra-stable, high-resolution spectroscopy, the ELT and its cousins could separate the faint spectral wobble of Teegarden star B from the glare of its red dwarf sun. Tiny shifts in specific absorption lines could reveal the planet's orbital motion, mass, and maybe even hints of its atmosphere. Here's the pattern interrupt. The first image we get of Teegarden star B might not look like a picture at all. It could be a barely there spectral line, nudged back and forth by the planet's orbit, telling us there is air, or that there is none.
Looking further ahead, concepts like LUVOIR or HABEX, with powerful coronagraphs, or even free-flying star shades, aim to block out the star's light and directly image nearby Earth-like planets. Around a dim red dwarf, the contrast is slightly more forgiving, and Teegarden star B is close enough that, on paper, such a mission could one day collect a true reflected light spectrum. So it's time to find out the truth about expectations. Even then, we will not see continents, oceans, or cities. We will see a single pale dot and a few broad spectral features, from which we infer clouds, surface temperature, and maybe biosignature gases. Optimistically speaking, that is still revolutionary. Teegarden star B is close, Earth mass, and in the Goldilocks zone. It will be one of the first places where we test our theories of red dwarf habitability against real data. And in the next section, we'll explore what those first hard-won measurements might actually tell us about the planet's fate. Teegarden star B versus TRAPPIST-1 and Proxima b. Who wins the habitability race? So if Teegarden star B will help test red dwarf habitability, how does it stack up against the current champions in that race, TRAPPIST-1 and Proxima b? In the hunt for alien life, these three systems are our closest, sharpest laboratories. So let's begin with a simple comparison, laid out in words instead of a table. Teegarden star is about 12.5 light-years away, an ultra-cool red dwarf that seems old and relatively quiet. TRAPPIST-1 sits farther at around 40 light-years, also an ultra-cool red dwarf, but with 7 tightly packed Earth-sized planets. Proxima Centauri is the nearest of all, at just over 4 light-years, a classic flare-prone red dwarf, and home to Proxima b. Now the planets themselves. Teegarden star B has a minimum mass extremely close to Earth's, and receives almost exactly Earth-like insolation, right in the Goldilocks zone. TRAPPIST-1e is also very Earth-like in size, and gets roughly 2/3 of Earth's light. Proxima b is a bit more massive than Earth, and is also in its star's habitable zone. On paper, all three look like promising, potentially habitable worlds. This means the details really matter.
It should be noted that TRAPPIST-1 has a huge observational advantage. Its planets transit. They regularly pass in front of their star, so JWST can directly probe their atmospheres. We already know that TRAPPIST-1b and c are essentially airless, and that 1e lacks a thick hydrogen envelope or Venus-like blanket.
Teegarden star B, by contrast, does not transit as far as we can tell, so we have no atmospheric detection yet, no direct data, just models. But while TRAPPIST-1 wins on sheer data, Teegarden star may win on stellar temperament. Its old, quiet red dwarf appears less active than TRAPPIST-1, and far less violent than Proxima. Proxima b is bathed in intense flares and high-energy radiation. Its atmosphere, if it ever had one, may have been stripped away. Teegarden star B, orbiting a calmer star at an Earth-like flux, looks, at least from the stellar side, more promising. Each system, then, is a different experiment in red dwarf habitability. TRAPPIST-1 lets us study multi-planet dynamics, tidal locking, and a whole family of atmospheres under one star. Proxima b shows us the extreme end of space weather, where life would have to survive constant stellar outbursts. Teegarden star B represents the quiet, ancient dwarf scenario, slow-burning stability over tens of billions of years. So it's time to find out the truth. We cannot crown a single winner yet, but Teegarden star B clearly belongs in the top tier of nearby worlds that could, in principle, host surface liquid water and maybe life. The real twist comes when we ask what those different environments would actually feel like on the surface, and what kinds of creatures, if any, could survive there. If we could visit colonies, challenges, and the long red future. So if Teegarden star B really can host liquid water, what would it actually mean to live there? Imagine we have solved the problem of getting across 12.5 light-years. We arrive in orbit around this dim red dwarf, and our target planet hangs below us. One face locked in eternal day, the other in endless night. Where do we build the first home for our species in this distant system? Most likely, we would head straight for the Terminator Zone, that thin ring of permanent sunrise. There, the star would hover motionless on the horizon, a deep red ember casting copper shadows. Habitats might be buried into the rock, like elongated arcs, aligned along the twilight line, to avoid both the scorching dayside and the frozen night. Outside, constant winds would roar from hot to cold, so every structure would be streamlined, anchored, and partly underground to survive a ceaseless atmospheric river. Inside, though, we would remake the sky. Human bodies expect a day-night rhythm. Without it, sleep, mood, and long-term health begin to unravel. This means every settlement would use carefully programmed lighting, cycling from bright white to deep red to darkness on a 24-hour schedule, even though the star itself never moves. It should be noted that if Teegarden star still throws occasional flares, the outer hulls would be layered with regolith, water, and magnetic shielding, turning colonies into low-slung, armored reefs clinging to the twilight. Energy and heat management would be very different from Earth. The day side could host vast solar farms facing the fixed red sun, delivering a constant power flow instead of a daily curve. Heat pipes might run toward the night side, dumping excess warmth into the darkness, while cables carry electricity back. In the hunt for alien life, we often imagine fragile atmospheres stripped away by radiation, but here we might deliberately sculpt the climate, using mirrors, shades, and even greenhouse gases to keep the Terminator band in the narrow Goldilocks zone of habitability. Optimistically speaking, the biggest advantage of Teegarden star is time. Red dwarf stars like this can burn steadily for hundreds of billions, even trillions of years. Our sun will be gone long before that, but a civilization rooted here could watch entire generations of sun-like stars live and die, while their own dim star barely changes. What kind of philosophy emerges when your sky promises near eternity? Culture under a fixed crimson sun would not feel Earth-like. Art might obsess over gradients of red and infrared shimmer. Stories could revolve around the forbidden extremes, the blazing substellar point and the lightless ice of the far side. Children might grow up thinking of direction not as north and south, but as toward the star and toward the dark.
Would concepts like morning and evening even make sense anymore once they are purely artificial? So it's time to find out the truth. Every one of these choices depends on the real environment. If Teegarden's star B has a thick atmosphere and oceans, we adapt to alien weather. If it is airless rock, we carve sealed caverns in vacuum. In the next part, we will dive even deeper into how such extreme conditions could shape not just our technology, but the very biology of any life that might call this strange world home. What we've learned about life under a red sun. So where does all of this leave us? If we step back from the details for a moment, what picture of Teegarden's star B and of life under a red sun really emerges? We started with a hidden neighbor, an ultra-cool red dwarf only about 12.5 light-years away, so faint it escaped notice until the early 2000s. From there, we followed the trail of radial velocity data to a planet almost exactly Earth mass, racing around its star in less than 5 days, yet somehow sitting in the Goldilocks zone with Earth-like levels of starlight. Along the way, we explored what that actually means on the surface. A likely tidally locked world, one hemisphere in endless red daylight, the other in eternal night, with a narrow twilight ring as the main candidate for a truly habitable strip. We imagined thick atmospheres shuttling heat around the planet, thin ones freezing out on the dark side, and exotic climates where clouds and oceans pile up under a dim, fixed star. In the hunt for alien life, the star itself is as important as the planet. It should be noted that Teegarden's star appears to be old and relatively quiet for a red dwarf, past its most violent youth. This means fewer catastrophic flares stripping atmospheres, and more stable conditions over billions of years. Compared with harsher neighbors like Proxima Centauri, that alone nudges Teegarden's system into a more hopeful category.
But while the star looks promising, the planet still holds its cards very close. We know Teegarden's star B has roughly Earth-like mass and receives roughly Earth-like energy. What we do not know is whether it kept a substantial atmosphere, whether that air is rich in greenhouse gases or thin and fragile, and how efficiently winds and oceans, if they exist, move heat from day to night. Those climate dynamics are the difference between a temperate world and a frozen, airless rock. Optimistically speaking, Teegarden's star B sits in a fascinating middle ground. It is not a guaranteed paradise with blue skies and continents under a gentle red sun, but it is not obviously doomed either, like scorched, ultra-hot planets or frozen mini-worlds we can already rule out. Small changes in starting water content, magnetic field strength, or early flare history could tip it toward lush habitability or permanent desolation. How many such knife-edge planets might be scattered through the universe? So it's time to find out the truth about what this means for us. Red dwarfs dominate our galaxy. If even a fraction of their Goldilocks zone planets can hold on to stable atmospheres, then life may be far more common than our sun-based intuition suggests. And if most of them fail, that tells us Earth's story is rarer and perhaps more fragile than we like to imagine. Even if we never walk Teegarden's star B, the exercise of picturing forests under infrared light or civilizations clustered along a permanent sunset forces us to stretch our sense of what a normal planet and a normal sky look like. In the next part, we will turn that thought experiment back on ourselves and ask what these strange red worlds are quietly revealing about our own very specific way of being alive under a yellow star. Your turn under the red sky. What should we explore next? We have imagined 3 very different worlds under that unmoving red sun. Which one feels most real to you? Is it the airless, bare rock where Teegarden's star B is little more than a tidally locked ember, its dayside baked and its nightside frozen with no atmosphere to soften the contrast? Is it the twilight ocean planet
with a thin, habitable ring of water and cloud forever circling the line between day and night? Or is it the steamy mini-Venus, wrapped in a crushing blanket of greenhouse gases, glowing dimly in the infrared? Tell us in the comments which version you find most compelling and why that particular planet speaks to you. In the hunt for alien life, these preferences matter more than they first appear. When you choose a favorite scenario, you are also choosing which physics, which climate models, and which histories you think are most plausible. So, let's begin a conversation down there. What kind of atmosphere do you think Teegarden Star B really has? And what would that mean for its sky, its weather, and its chances of being truly habitable? Then, take it one step further. If life has found a way under that red dwarf, what does it look like? Do you picture slow-growing, infrared harvesting forests along the Terminator? Or compact cities hugging the permanent sunset, built by civilizations that have never seen a true night or a true noon? And if an alien astronomer there pointed a telescope at our solar system, what story would they tell about a small blue dot orbiting a bright yellow star in the middle of its own Goldilocks zone? It should be noted that this is not our first visit to compact red dwarf systems. If you want to keep traveling, we have deep dives on TRAPPIST-1 and its 7 Earth-like worlds, and on Proxima b, the nearest potentially habitable exoplanet to Earth. We also explore what the James Webb Space Telescope is actually seeing when it measures starlight filtering through distant atmospheres, and how that data lets us rule out or rescue different versions of these planets. Optimistically speaking, we are at the very beginning of this story, so it's time to find out the truth with better instruments, better models, and better questions. If you want more of these focused, model-driven tours of specific exoplanets, the tools we use to study them, and what they might teach us about life in the wider universe, consider subscribing, liking this video, and sharing it with someone who also wonders what might be living under a red sun. Because somewhere, under a star that never moves in the sky, there may already be eyes looking back at us. This means that every new telescope we build is not just a better way of seeing out, but a better chance of being seen. And if Teegarden Star B is watching right now, what do you think they're about to discover about us next?